Good afternoon. Mathematics gives us hope that every problem has a solution. Myself, Supriya Naika, MK, hosting this program. I welcome one and all for 77th episode of Creative Online Talks. December 22nd, every year is celebrated as National Mathematics Day in India. It is the birth anniversary of legendary mathematician Srinivasa Ramanujan. In 2012, the Prime Minister Manmohan Singh declared December 22nd as National Mathematics Day to honor the life and achievements of Ramanujan. On this occasion of National Mathematics Day, Creative has organized a lecture on number theory today. To present this, we have Sri T. Venkatesh sir with us today. Before start, I like to brief about Creative. Creative is a group of people who are eager to gain new knowledge. Creative, cre means creativity, active means activeness. Creative keeps us active. Knowledge square is our tagline. Sharing of knowledge increases our knowledge. Vision of Creative is to build constructive thinking on various domains. Our main focus on non-textual, non-academic, non-syllabus related concepts. Creative is a platform to the resource person to share their views, discoveries, results, analysis, and many more. And we are thankful to all our resource persons for accepting our invitations and engaging us with their knowledge. Every Saturday, we are organizing online talks on Saturday around 3 to 4 p.m. On Zoom platform, and also we live streaming in our YouTube channel Creative GBD. I welcome one and all for today's session, and I call Afrin Taj to give introduction about today's speaker. Over to Afrin.
Yes, ma'am. Good afternoon to everyone. Myself, Afrin Taj, paying an immense pleasure to introduce today's speaker, Professor T. Venkatesh, sir, Director, Mathematical Science Institute, Belgavi. Sir, native in Hospete, schoolings and graduated in BSc, Vijayanagara College in mathematics, done his master's and pursued in PhD from Karnataka University, Dharwad. He joined Karnataka University Service in the year 1983 at its Belgaum campus till 2010. Later, the center was separated from KUD and upgraded into an independent university named after Rani Channamma of Kittur. There, he worked for remaining period and retired from RCU in 2019. From January 1st, 2022 as a Director of Mathematical Science Institute, Belgavi. Such passionate about professional career to teach and undertake research at all levels, and took a volunteer to improve the quality of the teachings in schools, colleges, and university department. He also organized several workshops, conference, and symposium, guided students for their doctoral studies. Now, as a director of institute, creating an ambition for good research to happen and assuring that the institute where the people can come and use the laboratory and interact with the peoples on offline and online. Sir is also active in visiting US and serving as scholar. So today we welcome you, sir, in the creative class. Over to Supriya, ma'am.
Thank you, Afrin. Thank you. Sir, over to you. Sir, mute agide. 1 minute. Yes, sir.
Yeah, I thank the organizers for the opportunity. And It's my pleasure to speak to the people who have joined this meeting and the objectives of the creative initiative. The first and foremost thing is that it's such an important occasion for all of us to celebrate and observe this National Mathematics Day to commemorate the birth anniversary of Srinivas Ramanujan, a rare gift from Kumbakonam, not only to India, to the rest of the world and the intellectual community. His life and work itself is a great inspiration for youngsters and budding mathematicians all over to emulate. So it is in this behest that we are all here to share some of the views that such great people have contributed to the stock of knowledge, and then which continue to impact and influence the even present generation people. So, well, I have titled this talk as Number Theory Today. Number theory in the present context. See, if you look at the way this pure part of mathematics, which even Gauss claimed that our gentle hand, if we lay our gentle hand on this theme, then he had an apprehension not to do that to make it dirt and unclean. But soon we realized that the myth that number theory, being a purest of pure mathematics, remained as a piece of exhibit proved to be otherwise most influential field for applications in cryptography, etc. And wherever you see the basic fundamental problems that we encounter in basic sciences and other diverse areas. So numbers ultimately speak. So, and then, and in the present context, again, you would see that we have to talk mathematics or number theory for that matter in the context of computers. Computers are there in the midst. We have to deal things, okay? So they have entered the realm of our discourse in a way. So that's why it is so apt to see what number theory in its present form is doing, the way the powerful theorems like Euclid's division algorithm, age-old one, even today, computers crunch whenever a software is run. So, and as such, mathematics is a theory builder. We all know that. And we felt that, especially in the 20th century and onwards, that mathematicians required areas like theoretical physics. It requires this kind of physics which have to be seen with the different physical laws for different time scales to describe the properties and processes of materials, whatever, or to describe the physical phenomena. So multi-scale methods and computation became a very driving force nowadays. So when I look at the time scale and the space-time continuum, so you would know that the first assumptions the physicists would make about this entire exercise is that they would assume the universe to be discrete and finite, even for that matter. But the abstract notion of mathematics is that numbers for ourselves, we assume that and infinity also is accommodated into our number systems. So even with starting with natural numbers, still we'll eventually look at this number infinity, which is totally a different kind of number. but we'll have to entertain them. That's why when we saw a nicely written historical life and work of Ramanujan, the book was titled as The Man Who Knew Infinity, something of that sort. Okay, so we can keep that in mind, that infinity also as a number with a different texture and in different way one has to perceive it. So that's the one thing. So as a theory builder, so theoretical physics became a limelight, especially when in the 20th century, maybe around. See, when we look at the lifespan of Ramanujan, 1887 to 1920. So around 1913, he sets his journey to join Hardy, his mentor and a passionate collaborator, where they collaborate for next 7 years there. So that's between 1913 and then 20. If you look at around that time, around 1905, Einstein comes up with this famous annus mirabilis, what we say today, special relativity theory papers. In that revolutionizes one aspect of it. And then his dream to unify gravity. Look at that span. There's a critical mass intersection between the pure works of mathematicians and then physicists on one hand. When I say mathematicians, I would naturally go back a bit because we have placed Ramanujan in the galaxy of Euler, Jacobi, Gauss. So what all these people did during their time. So Riemann, for example. See, Gauss himself gives an estimate for the primes when he is around 14 years or somewhere around that. So, but integral calculus is in full swing with Newton developing calculus. Leibniz and Newton both independently do that thing. So these are all very interesting developments that happened around same time. See, Ramanujan was different in many respects because of his background. As we all know, that this guy was not even formally had his education beyond intermediate, which he could not complete. The only thing that he did was mathematics. So luckily for him, people supported in whatever way they could do back home in India. And now his prayers also could prove to be on his side. So Hardy invited him. So that is the real thing one would see a decisive step. Gives us a kind of energy. That's what even I keep telling some of the people in the present generation, especially students who are widened apart in different parts of rural pockets of our schools and colleges. They need not feel desperate because when Ramanujan could do it some 130 years back, all this in the absence of computers or technology, information technology, there is no way to access information or communicate except the traditional postal services inland and outside. But still, people appreciated that. So, and then that's how some of his work came to light. That's one thing. And the second thing that I would notice is, had Ramanujan lived for long, because he was known for in the records, we see that this gentleman at the very early age he started recording all his problems that came in his mind, jotted down them in a notebook like thing. So by the time when he exit um, uh, from the life, from this world, more than 25,000 conjectures, Ramanujan conjectures or problems were left to the posterity. This is a very what I would say stupendous way of any individual doing it. So, and now much water has flown under the Ganges. today we see, as I said, we are computers into the arena. So the whole complexion of doing mathematics has changed within no time. What happened in the first 50 years, something like that, if you look at in the last century, and then later on afterwards. So these are all very probing things, exciting developments that we need to really take them into account. So now what I see is what is happening with the number theory itself. How does the Ramanujan would appear in this in this new era of mathematics, which we talk, which is very sophisticated tools and techniques. Somebody talks about L functions, and the Ramanujan really knew L functions are not automorphic forms and all those things, by using these computers for computing, and then come up with the great works of Ramanujan himself and to make it a reality. So because the industry is also seeing a lot of potential in basic research that has gone into theoretical studies of mathematics, physics, and computer science. So that is why it should keep the burner burning. So whatever that was there on the back of the burner has come onto the forefront. So we are on the central stage. Mathematics is on the central stage, and therefore it required many disciplines, and also many disciplines are depending on some of the problems that are still open, are unable to come out of their from their this one shades. So how mathematics can really help build a better bridges connecting the gaps between one end of the problem to the other in different disciplines. Within mathematics itself is one thing. Okay. So these are some of the things that I was thinking I should be able to throw some light on this kind of a situation like this. So in my talk, I have come out with the two areas. Okay, because one is that computers is one thing, and computer science. The other one is the industry. Why industry is also looking at some of the things. See, what really interests a mathematician, if you are a hardcore pure mathematician, what would interest is, for that matter, equations and numbers. Okay. So, and then solve them, and then get some solutions. So if you look at the number theory, the way it shaped some of the problems, combining algebra, geometry, that is, I can say that the Diophantine equations are the best examples. Okay, from the days of Diophantus of Alexandria, 3rd century BC again. Okay, and then people were trying to solve equations for their integer solutions. And that's why they named it after Diophantus. So such equations and problems relating to them were known as Diophantine problems or Diophantine equations. Okay, and so and then the story runs like this. Where by the time when Fermat looks at the works of Bachet, translated works of Bachet during his time in 1640s or somewhere around that, Fermat would figure. Then his famous Fermat's last theorem is a classic example of a Diophantine problem, generalizes for higher exponents, the Pythagoras theorem. Can we have integer solutions as triples x, y, z such that x rise to n, s, y rise to n is equal to z rise to n? That's the thing. As we all know that it remained for long as an unsolved problem. People working on the problems, contributed a great deal of connecting, supporting things, and then so the subject itself graduated thoroughly, and a lot of subsidiary branches were took birth in the attempts to solve these problems. Okay, so algebraic geometry, is one big area where we even today we see that the attempts to solve them. Okay. Ultimately, it was Andrew Wiles around in the late 90s, the earlier century, 20th century, around 1993, somewhere around that. He comes up with the solution to this problem. And ultimately, he sees the fate of the Fermat's last theorem, which becomes a last Fermat's last theorem, which was a conjecture as a marginal note left by Fermat himself. Okay. And now, when I say that solving equations with numbers is one thing, okay, and then the on the other side, because the computers were used to get the final word, as we say. See, mathematicians would state a theorem. When you put it to running those statements into translate them to crunch numbers and all those things. So a device is required. Either we should be able to do it on our own, or now computers are helping us to as devices to do those things, and therefore computers as a device, computing device, has helped us to demonstrate the effectiveness of the efficient algorithms that were developed by the people. So what is this area of mathematics, or one would say, in contrast to what we can claim otherwise in the realm of pure mathematical discussions. To me, this means that mathematics also required theoretical computer science on the maybe on the lines of theoretical physics. See, because I said theoretical physics means quantum mechanics. Again, quantum mechanics problem, quantizations, and all those things at that scale, and then supporting equations like Schrodinger wave equations at 10 raised to minus 15 seconds, femtoseconds, they say. And then you go Boltzmann's. So scale is another thing, and then at 1 second, you say the fluid mechanics problems. If you look at the PDEs, okay, Navier-Stokes equations for smooth solutions. So some of them figure, even now we talk about some of these problems coming from classical era of mechanics into quantum mechanics as some unsolved problems, and some even figure in Millennium Prize problems, where it really throws a challenge to the inquisitive young minds. So in that context, we bring in theoretical computer science into our discourse. So here, people started making connections with number theory with the discrete problems and discrete methods. So I was just going through a very interesting interview of Lavash, a well-known, renowned discrete mathematician, and his collaboration with Avi Wigderson. Both were awarded for their collaborative work in their own field and coming together, working on discrete mathematics and theoretical computer science areas. So they see that the P versus NP problem. That's where it starts popping up into this area of mathematics. So Turing's notion of what is today called as a Turing machine captures the intuitive of an effective procedure, and so to say sets the standards for what can be computed. See, when we see ultimately we have a device, and then see this is also another thing. See, the way the quantum mechanics used mathematics is one thing, because the status of physics as a knowledge in science was already an established fact. For computer science, it had to develop and acquire that status, and therefore, whatever that were coming up in computer science to develop itself into a theory, a knowledge, but it required for its development, and therefore it was unwise for mathematics to grab from that. So that happened with physics. But for computer science, for some time, computer science itself used whatever that it could produce for itself to take the pride of becoming and enjoying the status of as a knowledge of science. And so, if you look at these things, we are justified in claiming that mathematics requires both theoretical physics and also theoretical computer science. And now the the demarcation is removed now, so they gel with each other. Okay, back and forth. This is what I would say. So then, if you look at the Turing machine, which is so fundamental and basic, see, there was something that we must recall here. So around that time, Hilbert's ambitious project. He had a dream. That's one thing that we should also take into account. See, both Poincare and Hilbert were friends. So when Poincare requested Hilbert to address the 1900 Paris Convention at ICM, International Congress of Mathematicians, they gather every 4 years. And so it was there Hilbert comes up with his famous 23 problems. And also he has Hilbert's formalism. So what is his dream is that it had two parts. One is everything that is true in mathematics is provable, and everything that is provable can be automatically computed. This is the first thing that he taught. So that is formalizing. So it's provable and then computable. Absolutely. Unfortunately, what happened? See, Gödel. So he is Kurt Gödel. So he is maybe around the same time, Hermann Weyl, Einstein, all these people, Oswald Veblen, they were all there at a great place where Institute for Advanced Study was established around that time, and they were all there. Okay, Kurt Gödel also a part of the faculty at the Institute for Advanced Study. So known for his famous incompleteness theorems, Gödel's incompleteness theorems, that he was the one who shattered the first one, the dream of Hilbert. So what does it say is that there are true facts. Let us say about integers, if you take, so that cannot be proven. So there are certain unprovable statements which are true. That's what, according to his version. Okay, what Hilbert claimed was it can be absolutely automatically computed and proved. No, that cannot happen. That is what is, there is an incompletion, however strong a formal system may be, and however strongly worded a formal system may be, there are certain statements which are true but cannot be provable. Okay. And then Church and Turing shattered the second myth. So, see, one must read this Turing's machine. So, his work, what Turing did, Turing's proof in doing these things. Okay. So, that then this remained as incompleteness in the first instance. Okay, and now what is this? What is the ultimate thing that was happening was, okay, on one hand you have a class of problems, okay, so um, uh, which were classified, and then there are some efficient algorithms, in the sense that if an algorithm that can be run in polynomial time, in the jargon of computational complexity parlance, okay, because computation is there, then the complexities of computing is also another thing. We know that, for that matter, suppose first thing that we encountered was with numbers itself. All right. So, is every real number computable? If I ask so. So, according to the Hilbert Formalism, his first claim itself says that it should be. We should be able to compute. There should exist an algorithm that should be able to compute that number, and therefore, we are done with that, and therefore, what about this incompleteness? Then there's a question of all that. So this P versus NP problem remained as a central core problem even today in theoretical computer science. Okay, and then around 70s, we start looking at them. Okay, I think Richard Karp fairly tries to address what is known as NP complete. Okay, so now the basic question is, if P versus NP is all about, is P is equal to NP, or are they one and same? There is no two distinct classes between the polynomial time algorithms and then non-polynomial time algorithms problems. So recently, when some of our Indians proved that the primality testing is in polynomial time. So these are number theory problems. See, though purely a number theory claims that we make, but we still see that it took a great deal of time for them. Computers were required to ultimately decide the fate of these problems. Now, in the same spirit, if I put it, Riemann hypothesis, say for example, because see, after all, see, we are looking at the fallout or the impact of number theories, right from Ramanujan and onwards, if you look at. So what did really went on when Ramanujan congruences were seen in some light for the estimates of number of primes in a given arithmetic progressions? Then one of the outstanding results that we could see of late around 2000, in the early decades of 2000, this passage of time. So tau green result theorem is an outstanding. The experts say that. So that's a very groundbreaking one. And even for that matter, Fermat's last theorem. And then, see, silently on the backdrop, you have a prime number theorem. Fermat's last theorem also did a splendid work, where two of our Indian origin young mathematicians won Fields Medal. All right. So that is also an interesting thing, that they are all Diophantine problems. So they extended Manjul Bhargav and then Akshay Venkatesh. So getting into the real stories of Ramanujan, making Ramanujan to revisit, see, all those things happened. So these are some of the things that we need to sharpen our memory. See, celebrating National Mathematics Day in this sense is just tell this present generation they are better equipped now And then the policymakers, governments, nations, and including the industry business houses can support them. So there are a lot of money coming in for people to work on this quantum computing to ultimately to come up with the quantum computers. So if you want to train youngsters in these sophisticated areas, okay, then which are the people? Who are the people, places? What sort of knowledge is required to prepare on their part, both for teachers and students, so that they will be in a position to understand and appreciate. See, the spirit of Ramanujan is that you appreciate and encourage, especially when we don't know. As in Kannada, there is a saying, "Yahutadalli yav havidiyo gottilla namige." But an honest attempt is required to invest in knowledge, to invest in time, and so that give them a kind of semblance or an ambience to work on those great ideas. So when I say Riemann hypothesis, okay, now the computers were there. So Andrew Odlikov and some of the people, okay, they really computed zillions of zeros of the zeta function to sit on the critical strip half line, but that doesn't solve the theorem itself. So what is the mathematical statement of Riemann hypothesis? Is that all the zeros of the zeta function lie on the critical line half, means they must lie on that whole line. So what sort of knowledge is required? We do not know yet. They're computing. See, numerically, computationally, using computers, they have generated zillions of zeros close in that strip to the critical line. But ultimate thing is interval half minus epsilon, half plus epsilon, for epsilon greater than 0 is one thing. But exactly for epsilon 0, that critical line is x is equals to half. So that should happen. So that is the ultimate result for the open problem. So it remains still open. So that is a Riemann hypothesis, the status of Riemann hypothesis. Now this is all because when I say number theory today means to prove even Fermat's last theorem, what happened in between was the elliptic curves came into prominence. So what are these elliptic curves? These cubics. So in the process, a Diophantine problem, because basically you have to solve integer solutions in a very generalized way to that problem. And therefore, the elliptic curve came to prominence, and then automorphic forms, modular forms, all those things were there. See, I don't want to go into all those technical aspects. It's for a novice. We can only appreciate by looking at Himalaya. If we want to really climb that, then you'll have to make a grand preparation for that. And one thing is that it enhances your confidence that Himalaya is not growing. The height is not going to go up, but your confidence really goes up when you start looking at the Himalayas closely and start climbing. That is the idea. That. So, but now look at these elliptic curves. They found their applications in cryptography, where day in and day out you swipe your ATM card so confidently that from your account only the money is going to the intended recipient, and vice versa, and that's how those security issues and all those things are thoroughly insulated. But still there are cyber crimes and all that. That's a different issue. But anywhere, everywhere, if you look at these things, the cyber crimes you can detect using this cryptic way, that you develop some encryption standards. Under that encryption standard, you develop systems in which you can transact, you can do business. So the whole information technology, IT related problems that depend on this basic knowledge of what is called as cryptography, crypto system. From where it is coming? It is coming from hardcore mathematics. Could be. So they say that it is not Alan Turing machine now, a universal computer. The other day, I was very interesting to know this. Before one day of Ramanujan's birthday, a nice article appeared in one of the daily newspaper that the people industry is talking about Ramanujan machine, Turing machine to Ramanujan machine. So that itself signifies the way we are heading towards in that direction. Okay, so when I say that Ramanujan congruences, okay, then he works for interesting things and gives a solid analytic bounds for the number of primes in a given arithmetic progression. What is that one simple congruence? If you take one expression just to tell you to get your appetite, so the partition numbers. So for any positive, if you have a natural number n, then in how many ways you can partition the number is one thing. So, and in such a way that the subparts should be in a non-increasing order. So if you take a small number like n is equals to 4, then P of 4 is 5. So for each n, you define P of n as a partition function on the set of positive integers. And then see, Ramanujan was looking at this part. Okay. See, after all, what mathematics wants us to do is patterns should emerge. So whenever there is a pattern, see, with natural numbers, the natural pattern is arithmetic progression, natural God-given arithmetic progression. But in general, if I can have an arithmetic progression, so you take that progression, and in that progression, we would like to see some interesting things. For example, I'm interested, you or anybody further is interested in primes. The prime numbers are those numbers which do not share divisors other than 1 and itself. So that's unique to its character, and therefore we are interested in them because they are the building blocks for any number composite. If it is not prime, then we say that it's composite. Okay. Now, deciding given any odd number, large odd number, whether it is prime or not is a primality problem. Deciding the status of its primality. So, like that, if you so how they are distributed. So you can get hold of a composite number, how they are distributed with their factors. But here, it doesn't help you. Okay. And therefore, how do I get an estimate for the number of primes? Is there any way, though they are sparsely distributed, it gives a feeling that after some stage, all the primes would exhaust, they repeat themselves, and therefore primes are finite. So that is not the thing. Euclid himself has said that primes are infinitude in number, and there are interesting proofs for that. And so they are infinite in number. Their distribution is funny, but yet you have a pattern in their distribution. And therefore, is there any way of giving an analytic expression? That is what mathematics is all about. That's the beauty of abstractions, and that's what it attracts you to number theory. And that's how people started liking this kind of investigation, so that it saves a lot of labor when they find their applications. Okay. So that took the toll, maybe in the beginning, but later on you see we are enjoying the comforts of those results by applying them in industrial applications and things like that. So these things, if I look at, say, for example, partition of a 5n plus 4 congruent to 0 mod 5. See, an expression, mathematical expression, if you know what is a P4 as 5, now I am generalizing this to P of 5n plus 4. To that 4, I am adding multiples of integral values 5n, P of 5n plus 4, congruent to 0 mod 5. So this is what Ramanujan was looking at, congruences, Ramanujan congruences for prime modulo. That is the thing. Now for n is equal to 0, 5n plus 4 is 4 itself. Therefore, my P of 4 is 5. So 5 is congruent to 0 mod 5. And now your 5n plus 4 for each integral n gives you an arithmetic progression AP. So you get hold of what I would say an estimate for in this progression. You go for primes. And now what can be said about for a quadratic equation? Supposing I say I'm just trying to give you a hint for youngsters to think about these problems. Okay? Suppose I have, instead of an plus b, I have my quadratic expression in place of that: an square plus bn plus c, p of an square plus bn plus c congruent to 0 mod p. That is what I want to look at. But if you put the values of n into this, I'm sure that you would get a bizarre kind of expression for the quadratic polynomial values. Certainly, they are not in any arithmetic progression. So, what is the factors that what is the use of trying for partitions of a quadratic expression? But there are quadratic congruences are there with respect to some dipendent problems. So that's a different issue. Okay, but I'm generally, if a novice would want to begin with a quadratic equation like expression like this, probably one sophisticated way, a soft way of opting out for this, and then going back to your Ramanujan congruences is just you put a condition that you look at its derivative. Now, if you differentiate this quadratic expression, the degree of the expression reduces by 1. So what you get into is a linear thing. So this linear one is in AP. So you go back to your Ramanujan. That's the thing. So even you can catch hold of some quadratic polynomial of degree 2, degree 3, etc. degree n. And then at each stage, you only come down to the linear aspect of the problem for partitions, and then you build up go back into the next level. Ultimately, you look at what partition of a number when substituted that integral value into the nth degree polynomial was wanting to. Is there any tunneling effect for this whole thing? This was an interesting problem that this was coming to my mind. Then I discussed it with some of my students, and then they thought that is there any way of extending this problem? That's one thing. And now, another interesting development that are taking place, where industry is really interested in, is 3D printing and mathematics of 3D printing. See here, as I said in the beginning, I started with numbers and equations and numbers. But here, equations and numbers are replaced by pixels. This is very interesting. These pixels would gel well with materials. So, and therefore, nowadays we see that the computer 3D printing computers, they are using this fundamental thing. It is equations with pixels for 3D printing. And so I think why people are working on these areas. These are all recent trends in math, and then looking at other areas for applications, especially industry. So industry supporting quantum computing, industry supporting 3D printing. So industry supporting many other areas for e-commerce and e-businesses is a testimony to what great people like Ramanujans and all this did at basic foundational research in the theorem themes like number theory, graph theory, etc., geometry. I think I will stop at this, okay? And that is how I would like to pay my tributes to Srinivas Ramanujan and want to celebrate National Mathematics Day in this fashion. And I thank for your time. There are anything that you want to discuss, I'll be happy to answer those questions to the best of my knowledge. Thank you. for your time.
Thank you, sir.
Yeah.
Any question from audience?
Sir?
Yeah.
Hello. Sir, what is your motivation to young mathematicians, sir?
What is this? What is your actually? What is young mathematicians? You mean?
Sir, ಅಂದ್ರೆ young mathematician ಗೆ ನೀವು ಎಂತ motivation ಕೊಡ್ತೀರಾ ಸರ್ ಅಂದ್ರೆ?
young
mathematicians ಗೆ ನಿಮ್ಮ motivation ಏನು ಸರ್ ಅಂದ್ರೆ?
ಸ್ಟೂಡೆಂಟ್ ಅಂತ ಹೇಳ್ಬೋದು ನಾವು. ಅವರಿಗೆ ಮೋಟಿವೇಶನ್ ಕೊಡಬೇಕು ಅಲ್ವಾ?
ಆಯ್ತು ಸರ್.
ಹೌದು. ಅದು ಮೋಟಿವೇಶನ್ ಕೊಡ್ಬೇಕು ಅಂದ್ರೆ ನೋಡ್ರಿ ಸರ್, ಅದು ನಮ್ಮ ಅದು ಕಲ್ಚರ್ ಆಗಿ ಬೆಳಿಬೇಕು. ಈಗ ನಾವು ಇದನ್ನು ಸಾಕಷ್ಟು ಏರಿಯಾದಲ್ಲಿ ನೋಡ್ತೀವಿ, ಮ್ಯೂಸಿಕ್ ಅಲ್ಲಿ ನೋಡ್ತೀವಿ. Lot of motivation we are giving. When it comes to mathematics, it is altogether a different ball game. ಈಗ ಮ್ಯೂಸಿಕ್ ಇಷ್ಟಪಡ್ತಾನೆ, ಸ್ಪೋರ್ಟ್ಸ್ ಇಷ್ಟಪಡ್ತಾನೆ ಹುಡುಗ. ಯಾಕಂದ್ರೆ ಚಿಕ್ಕ ಮಕ್ಕಳಿಗೆ ಮ್ಯೂಸಿಕ್, ಸ್ಪೋರ್ಟ್ಸ್ ಅವೆಲ್ಲ ಏನಾಗುತ್ತೆ, ಅವ್ರ ಏಜು, ಅವ್ರ ಹುರುಪಿಂದ ಓಡ್ತಾರೆ. ಅವ್ರ ಸೆಲೆಬ್ರಿಟೀಸ್ ಅವ್ರ ಮುಂದೆ ಇರ್ತಾರೆ. ಅವ್ರಿಗೆ ನಾನು ಈ ತರ ಆಗ್ಬೇಕು, ನಾನು ತೆಂಡೂಲ್ಕರ್ ತರ ಕ್ರಿಕೆಟರ್ ಆಗ್ಬೇಕು, ಹೀಗೆ ನಾನು ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ ತರ, ನಾನು ಮಂಜುಲ್ ಭಾರ್ಗವ ತರ ಆಗ್ಬೇಕು, ರಾಮಾನುಜನ್ ತರ ನಾನು ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ ಆಗ್ಬೇಕು ಅನ್ನೋ ಮೋಟಿವೇಶನ್ ಬರಬೇಕು ಅಂತಂದ್ರೆ ಅದಕ್ಕೆ ನಾವು ಮೇಷ್ಟ್ರುಗಳಾದವರು ಸ್ಕೂಲಲ್ಲಿ, ಕಾಲೇಜುಗಳಲ್ಲಿ, ಯೂನಿವರ್ಸಿಟಿಗಳಲ್ಲಿ, ಆಮೇಲೆ ಮನೆಗಳಲ್ಲಿ ಆ ಮಕ್ಕಳಿಗೆ ಅದ್ರದ ಒಂದು ಅಭಿರುಚಿ ಹುಟ್ಟಿಸ್ಬೇಕಾಗತ್ತೆ. ಅನ್ಫಾರ್ಚುನೇಟ್ಲಿ ಇಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ, ನಾವು ನಮ್ಮ ಮಕ್ಕಳಿಗೆ ಪೇರೆಂಟ್ಸ್ ನೋಡಿ, ಸ್ಕೂಲ್ಸ್ ಕೂಡ ನೋಡಿ, ನೀವು ಇಂಟರ್ನ್ಯಾಷನಲ್ ಸ್ಕೂಲ್ಸ್ ಅಂತ ಮಾತಾಡ್ತೀವಿ, ಅಲ್ಲಿ ಆ ಮಕ್ಕಳಿಗೆ ಆ ಮೇಷ್ಟ್ರುಗಳು, ಆ ಶಾಲೆಗಳಿಗೆ ಮೇಷ್ಟ್ರುಗಳು ಏನ್ ಹೇಳ್ತಾರೆ ಅಂದ್ರೆ, ನಾವು ನಮ್ಮ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ 3ನೇ ಕ್ಲಾಸ್ 4ನೇ ಕ್ಲಾಸಿಂದ ಕೋಡಿಂಗ್ ಹೇಳ್ಕೊಡ್ತೀವಿ ಅಂತ ಹೇಳ್ಕೊಡ್ತಾರೆ. ಗಣಿತ ಹೇಳ್ತೀವಿ ಅಂತ ಹೇಳೋದೇ ಇಲ್ಲ. ನಾವು ಅರ್ಥಮೆಟಿಕ್ ಬೇಸಿಕ್ಸ್ ಅವೆಲ್ಲ ನಾವು ಫೌಂಡೇಶನ್ ಹಾಕ್ತೀವಿ ಅನ್ನೋ ಹೇಳಿದ್ರ, ಅವ್ರಿಗೆ ಕೋಡಿಂಗ್ ಕಲಿಸ್ತೀವಿ, ಕಂಪ್ಯೂಟರ್ ಯಾವ ತರ ಆಪರೇಟ್ ಮಾಡ್ಬೇಕು ಅನ್ನೋದನ್ನ ಹೇಳ್ಕೊಡ್ತೀವಿ ಅಂತ ನಾವು ಆ ವಯಸ್ಸಿನಲ್ಲೇ ನಾವು ತಲೆಯಲ್ಲಿ ಏನೇನೋ ತುರುಕ್ ಬಿಡ್ತೀವಿ. ಅದು ಬಹುಶಃ ನಮ್ಮ ಭಾರತ ದೇಶದಲ್ಲಿ ಅತಿಯಾಗಿದೆ. ಈಗ ನಾನು ಪೌಲ್ ಎರ್ಡಿಶ್ ಹೇಳೋ ಪ್ರಕಾರ, ಒಬ್ರು ಹಂಗೇರಿಯನ್ ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ ಅವ್ರಿದ್ರು, ಅವರು ಒಂದು ಇಂಟರ್ವ್ಯೂ ನಲ್ಲಿ ಹೇಳ್ತಾ ಇದ್ರು, ಹೆಂಗಿದು ಹಂಗೇರಿ ಕುಡ್ ಪ್ರೊಡ್ಯೂಸ್ ಗ್ರೇಟ್ ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ಸ್ ಅಂತ. ರೂಬಿಕ್ನು ಅಲ್ಲಿಂದಾನೇ ಬರ್ತಾನೆ ಇವರೆಲ್ಲ. ಎರ್ಡಿಶ್ ಅವ್ರು ಹೇಳಿದ್ರು, ನಮ್ಮ ದೇಶ ತುಂಬಾ ಬಡ ದೇಶ, ಇಲ್ಲಿ ನಮಗೆ ದುಡ್ಡು ಹಾಕಿ ಲ್ಯಾಬೊರೇಟರಿಗಳು ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡ್ಬೇಕಂದ್ರೆ ಅಷ್ಟು ದುಡ್ಡಿಲ್ಲ ದೇಶದಲ್ಲಿ. ಆದ್ರೆ ಲೀಸ್ಟ್ ಇನ್ವೆಸ್ಟ್ಮೆಂಟ್ ಯಾವ್ದಕ್ಕಿದೆ ಅನ್ನೋದನ್ನ ನೋಡ್ಕೊಂಡು ಅದನ್ನ ಮಾಡ್ತಾ ಇದ್ರು. ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ ನೋಡಿ, ಇನ್ವೆಸ್ಟ್ಮೆಂಟ್ ವೈಸ್ ವೆರಿ ಲೀಸ್ಟ್, ಅಲ್ಲಿ ನೀವು ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡೋದ್ ಬೇಕಾಗಿಲ್ಲ. ಈವನ್ ಇಫ್ ಯು ಸೇ ಥಿಯರಿಟಿಕಲ್ ಫಿಸಿಕ್ಸ್ ಅಂತ ಮಾತಾಡಿದ್ರೆ, ಇಟ್ ಇಸ್ ಒನ್ ಕೈಂಡ್ ಆಫ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ವೇರ್ ಇನ್ ಲೈಕ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್ ಆರ್ ಚೀಪ್. ನೀವು ಒಂದು ಗುಂಡು ಪಿನ್ ಕೊಂಡ್ಕೊಳ್ಳೋದು ಬೇಕಾಗಲ್ಲ ನಿಮಗೆ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ. ಒಂದು ಒಂದು ಪೆನ್ಸಿಲ್ ಕೊಟ್ರೆ ಮಾಡ್ಕೋಬಹುದು. ಆ ತರ ನಮಗೆ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ ಇಂಟ್ರೆಸ್ಟ್ ಹುಟ್ಟಿಸಿದ್ರು. ನಾವೆಲ್ಲ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಓದ್ಬಿಟ್ವಿ. ಅಂಡ್ ದಟ್ಸ್ ಹೌ ಇಟ್ ಆಲ್ಸೋ ಇಂಪ್ರೂವ್ ದಿ ವೆಲ್ತ್ ಆಫ್ ದಿ ನೇಷನ್. ಸೊ ಇದು ನಾವು ಇಲ್ಲಿ ನೋಡಿ, ನ್ಯಾಷನಲ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಡೇ ಅಂತ ಇವತ್ತು ಸೆಲೆಬ್ರೇಟ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ನಮ್ಮ ದೇಶ 150 ಬಿಲಿಯನ್ 1.5 ಬಿಲಿಯನ್ ಪಾಪ್ಯುಲೇಷನ್ ಇರುವಂತ ದೇಶ. ಎಷ್ಟು ನಾನು ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಪ್ರೊಫೆಸರ್ ಆಗಿ 40 ವರ್ಷ ಆಗಿ ಕೆಲಸ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಇದೇ ಊರಲ್ಲಿ ಇದ್ಕೊಂಡು. ನನಗೆ ಒಂದು ಕಾಲೇಜ್ ಅಥವಾ ಒಂದು ಶಾಲೆಯಿಂದ ಫೋನ್ ಬಂದಿಲ್ಲ, ನಾಳೆ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಡೇ ಇದೆ, ಬನ್ನಿ ಮೇಷ್ಟ್ರೆ ನಮ್ಮ ಹುಡುಗರಿಗೆ ಏನಾದ್ರು ಮಾತಾಡಿ ಅಂತ ಹೇಳಲಿಕ್ಕೆ. ಇದು ಒಂದ್ ಸ್ವಲ್ಪ ನೋವನ್ಸತ್ತೆ ನನಗೆ. ಐ ಆಮ್ ಸಾರಿ ಟು ಸೇ ದೀಸ್ ಥಿಂಗ್ಸ್. ಈಗ ನೀವು ಕ್ರಿಯೇಟಿವ್ ಮಾಡಿದಿರಲ್ಲ, ನನಗೆ ಕರೆದಿದ್ದೀರಿ, ನಾನು ಇದು 4ನೇ ನಂದು ಲೆಕ್ಚರ್ ಕೊಡೋದು. ಇದು ನನಗೆ ಅಂದ್ರೆ ಆ ಒಂದು ಆಸಕ್ತಿ ನಾವು ಬೆಳೆಸ್ಬೇಕಾಗತ್ತೆ ಹುಡುಗರಲ್ಲಿ. ಆಮೇಲೆ ಕೀಳರಿಮೆ ಹೋಗ್ಬೇಕಾಗತ್ತೆ. ಈಗ ಇಂಜಿನಿಯರಿಂಗು, ಡಾಕ್ಟರು ಅಂತ ತಲೆಯಲ್ಲಿ ಹಾಕ್ಬಿಡ್ತೀವಿ ಅವರಿಗೆ ನಾವು ಮೊದಲಿಂದ. ಅದಿಲ್ಲ, ಅದು ಆಗ್ತಾರೆ ಮೊದಲು ಆ ಹುಡುಗನಲ್ಲಿ ಗಣಿತದ ಆಸಕ್ತಿ ಇದೆಯಾ, ವಿಜ್ಞಾನದ ಆಸಕ್ತಿ ಇದೆಯಾ, ವಿಜ್ಞಾನ ಗಣಿತ ಓದಿದ್ರೆ ಆ ಹುಡುಗನಿಗೆ ಫ್ಯೂಚರ್ ಇದೆಯಾ. ಸೊ ಎವ್ರಿಬಡಿ ಹ್ಯಾಸ್ ಟು ಥಿಂಕ್ ಆನ್ ದಿಸ್ ಟೈಮ್. ಅವಾಗ ಮಾತ್ರ ಸಾಧ್ಯ. ಇಲ್ಲ ಅಂತಂದ್ರೆ ಇದು ಸ್ವಲ್ಪ ನೀವ್ ಹೇಳಿದಾಗೆ 1000 ವರ್ಷ ಬೇಕಾಯ್ತು ರಾಮಾನುಜನ್ ಹುಟ್ಟಕ್ಕೆ, ಇನ್ನು ಎಷ್ಟು 1000 ವರ್ಷಗಳು ಬೇಕೋ ಮತ್ತೊಂದು ರಾಮಾನುಜನ್ ಹುಟ್ಟಕ್ಕೆ. ಸೊ ದಟ್ ಇಸ್ ದ ಥಿಂಗ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಒಳ್ಳೇದು.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
Any more questions? ಸರ್, ರಾಮಾನುಜಂ ಅವರ ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ಸ್ ಬಗ್ಗೆ, ಅವರ ನಂಬರ್ ಥಿಯರೀಸ್ ಬಗ್ಗೆ ಸಾಕಷ್ಟು ಮಾಹಿತಿ ಕೊಟ್ರಿ. ಅವರ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಅಲ್ಲಿ ಯಾವ್ದಾದ್ರು ಒಂದು ಇನ್ಸಿಡೆಂಟ್ ಶೇರ್ ಮಾಡಕ್ಕೆ ಆಗುತ್ತಾ ಸರ್? ಯಾವ್ದಾದ್ರು ಒಂದು ಇನ್ಸಿಡೆಂಟ್?
ಅದೇ ಅದು ಟ್ಯಾಕ್ಸಿ ಕ್ಯಾಬ್ ನಂಬರ್ ಅದು 1729 ಒಂದೆಲ್ಲ ಹೇಳ್ತಾರೆ. ಅದು ಒಂದು. ನೆನ್ನೆ ನಾನು ಅದೇ ಕೆನ್ ಓನೋ ಅವರು ಅಲ್ಲಿ ಜಪಾನ್ ನಲ್ಲಿ ಇದ್ದಾರೆ, ಅವ್ರೇನೋ ಟೂರ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಅವರು ಅಲ್ಲೊಂದು ಟ್ಯಾಕ್ಸಿ ಕ್ಯಾಬ್ ಅದು 1729 ಹಾಕಿದ್ರು. ಸೊ ಅದು ಒಂದು. ಅಂದ್ರೆ ನನಗೆ ನೋಡಿ, ಇವಾಗ ಎಕ್ಸ್ಪ್ಯಾಂಡರ್ಸ್ ಅಂತ ಮಾತಾಡ್ತಾರೆ ಇಲ್ಲಿ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ. ಅವ್ರು ಅದಕ್ಕೆ ಏನ್ ಹೆಸರು ಇಟ್ರು ಗೊತ್ತಾ? ರಾಮಾನುಜನ್ ಗ್ರಾಫ್ಸ್ ಅಂತಾನೆ ಇಟ್ರು ಹೆಸರು. ಹೌ ಟು ಫೈಂಡ್ ಎಕ್ಸ್ಪ್ಯಾಂಡರ್ಸ್ ಅಂತ ಒಂದು ವೆರಿ ಸ್ಪೆಕ್ಟ್ರಲ್ ಗ್ರಾಫ್ ಥಿಯರಿಯಲ್ಲಿ ನಂಬರ್ ಥಿಯರಿ ಪ್ರಾಬ್ಲಮ್ಸ್ ಬರುತ್ತೆ. ಬಹಳ ದೊಡ್ಡ ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ಸ್, ಪೀಟರ್ ಸರ್ನಾಕ್, ಆಮೇಲೆ ಈ ಲೋವಾಸ್ ನಾ ಹೇಳಿದ್ನಲ್ಲ, ಇವರೆಲ್ಲರೂ ಇವನ್ ಆವಿ ವಿಕ್ಟರ್ಸನ್, ಸಾಕಷ್ಟು ಜನ ದಿ ಟಾಕ್ ಆನ್ ರಾಮಾನುಜನ್ ಗ್ರಾಫ್ಸ್, ಹೌ ಟು ಕನ್ಸ್ಟ್ರಕ್ಟ್ ರಾಮಾನುಜನ್ ಗ್ರಾಫ್ಸ್. ಅದು ಯಾತಕ್ಕೆ, ವೈ ವಾಟ್ ಇಸ್ ದ ಸಿಗ್ನಿಫಿಕೆನ್ಸ್ ಆಫ್ ರಾಮಾನುಜನ್ ಗ್ರಾಫ್ಸ್ ಅಂದ್ರೆ, ಇನ್ಫಾರ್ಮೇಶನ್ ಇದರಲ್ಲಿ ಸೌಂಡ್ ನೆಟ್ವರ್ಕ್ ಅನ್ನು ಹೇಗೆ ಡೆವಲಪ್ ಮಾಡಬಹುದು, ಎಫಿಷಿಯಂಟ್ ನೆಟ್ವರ್ಕ್ ಡೆವಲಪ್ ಮಾಡಿ ಇನ್ಫಾರ್ಮೇಶನ್ ನೆಟ್ವರ್ಕ್ ಥ್ರೂ ಮೂಲಕ ನಾವು ಹೇಗೆ ಅಷ್ಟು ಎಫಿಷಿಯಂಟ್ ಆಗಿ ಇನ್ಫಾರ್ಮೇಶನ್ ನಾವು ಎಕ್ಸ್ಚೇಂಜ್ ಮಾಡ್ಕೋಬಹುದು ಅಂತ ಒಂದು ಎಕ್ಸ್ಪ್ಯಾಂಡರ್ಸ್ಗೆ ಅವರು ದೇ ಕಾಲ್ ಇಟ್ ಆಸ್ ರಾಮಾನುಜನ್ ಹೆಸರಿಟ್ರು. ಆಮೇಲೆ ಹೀಗಳಿದಲ್ಲ, ಇಂಡಸ್ಟ್ರಿ ಕೂಡ ಎಲ್ಲೋ ಮೊನ್ನೆನೇ ಓದ್ತಾ ಇದ್ದೆ, ಅದಿನ್ನೂ ನನಗೆ ಹೆಚ್ಚು ಮಾಹಿತಿ ಸಿಕ್ಕಿಲ್ಲ. ರಾಮಾನುಜನ್ ಮಷಿನ್ ಅಂತ ಇಟ್ಟು ಅವರು ಮಷಿನ್ ಲರ್ನಿಂಗ್ ಅಂತ. ಮತ್ತೆ ಏನ್ ಮಷಿನ್ ಲರ್ನಿಂಗ್ ಅಂದ್ರೆ ಹೇಳಿ ನೀವೇ? ಏನ್ ಮಷಿನ್ ಏನಾದ್ರು ಲರ್ನ್ ಮಾಡತ್ತಾ? ಇಲ್ಲ. ನಾವು ಸ್ವಿಚ್ ಒತ್ತಬೇಕು, ನಾವು ಬಟನ್ ಒತ್ತಬೇಕು, ನಾವು ರನ್ ಮಾಡೋ ಅಲ್ಗಾರಿದಮ್ ಪ್ರತಿ ಒಂದನ್ನು ನಾವು ಅದಕ್ಕೆ ಫೀಡ್ ಮಾಡಬೇಕು. ಮಾಡಿದಾಗ ಆ ಮಷಿನ್ ಲರ್ನ್ ಮಾಡತ್ತೆ ಅಂತ, ಲರ್ನಿಂಗ್ ಮಷಿನ್ ಅಂತ. ಅಂಡರ್ ಸೂಪರ್ವೈಸ್ಡ್ ಲರ್ನಿಂಗ್ ಅಂತ ಈಗ ಆರ್ಟಿಫಿಷಿಯಲ್ ಇಂಟೆಲಿಜೆನ್ಸ್ ನಲ್ಲಿ ಇಂಟರ್ನೆಟ್ ಆಫ್ ಥಿಂಗ್ಸ್ ಅಂತ ಮಾತಾಡ್ತೀವಿ, ಡಾಟಾ ಅನಾಲಿಟಿಕ್ಸ್ ಅಂತ ಮಾತಾಡ್ತೀವಿ, ಡಾಟಾ ಮೈನಿಂಗ್ ಅಂತ ಮಾತಾಡ್ತೀವಿ. ಇವೆಲ್ಲ ಈಗ ಯಾತಕ್ ಮಾತಾಡ್ತಾ ಇದ್ದೀವಿ ಅಂದ್ರೆ, ಆ ಪೊಸಿಷನ್ ನಲ್ಲಿ ನಾವು ಇದ್ದೀವಿ ಅಂತ ಹೇಳ್ಬೇಕು. ಬಿಕಾಸ್ ಇಟ್ ಇಸ್ ದಿ ಇಂಪ್ಯಾಕ್ಟ್ ಆಫ್ ನಂಬರ್ ಥಿಯರಿ ಆರ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಆನ್ ಟೆಕ್ನಾಲಜಿ. ಅದರಿಂದ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಗೆ ಈ ಥಿಯರಿಟಿಕಲ್ ಕಂಪ್ಯೂಟರ್ ಸೈನ್ಸ್ ಬೇಕಾಯ್ತು, ಅದ್ರ ನಾ ಹೇಳಿದ್ದು. ಥಿಯರಿಟಿಕಲ್ ಫಿಸಿಕ್ಸ್ ಬೇಕಾಯ್ತು. ಆಮೇಲೆ ನೋಡಿ 3D ಪ್ರಿಂಟಿಂಗ್ ಅಂತೂ ನನಗೆ ಆಶ್ಚರ್ಯ ಆಗುತ್ತೆ. ನೀವು ಇವತ್ತೇ ಸುಮ್ಮನೆ ಆದ್ಮೇಲೆ ಪ್ರೋಗ್ರಾಮ್ ಆದ್ಮೇಲೆ ಈ ಛತ್ರಪತಿ ಶಿವಾಜಿ ಮಹಾರಾಜ್ ಟರ್ಮಿನಸ್ ಮುಂದಿಂದು ಒಂದು ಪಿಕ್ಚರ್ ಹೊಡಿರಿ ನೀವು, 3D ನಲ್ಲಿ ನಿಮ್ಗೆ ಅವೆಲ್ಲ ಬರುತ್ತೆ, ಟೆಸಿಲೇಷನ್ಸ್ಗಳು, ಬ್ಯೂಟಿಫುಲ್ ಪಿಕ್ಚರ್ಸ್ ಬರುತ್ತೆ ನಿಮ್ಗೆ. ಸೊ ದೇರ್ ಆರ್ ಸೋ ಮೆನಿ ಥಿಂಗ್ಸ್. ನೀವು ಈ ಒಂದಲ್ಲ, ಈ 108 ತಗೊಳ್ಳಿ ನೀವು. ಅಲ್ಲೆಲ್ಲ ಕ್ಯಾನ್ಸರ್ ಸೆಲ್ಸ್ ಹೇಗೆ ಮಲ್ಟಿಪ್ಲೈ ಆಗತ್ತೆ ಅಂತ ರಾಮಾನುಜನ್ ಕೊಟ್ಟಂತ ಕೆಲವೊಂದು ರಿಸಲ್ಟ್ಸ್ ತಗೊಂಡು ಅದನ್ನ ದೇ ಆರ್ ಏಬಲ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಹೌ ದಿಸ್ ಕ್ಯಾನ್ಸರ್ ಸೆಲ್ಸ್ ಆರ್ ಮಲ್ಟಿಪ್ಲೈ ಅನ್ನೋದನ್ನು ಮಾಡಿದ್ದಾರೆ ಅಂತ ನಾನು ಕೇಳಿದ್ದೀನಿ, ಓದಿದ್ದೀನಿ ಒಂದು ಕಡೆಗೆ. ಸೊ ಐ ಥಿಂಕ್ ನೀವ್ ಹೇಳಿದಾಗ ಚಿಕ್ಕ ಮಕ್ಕಳು ಇದನ್ನ ಇಂಟ್ರೆಸ್ಟ್ ತಗೋಬೇಕಾಗತ್ತೆ. So that budding mathematicians can India present such guys. ಇವತ್ತು ಶುರು ಮಾಡ್ಕೊಂಡ್ರೆ ಇನ್ನೊಂದು 25-30 ವರ್ಷಕ್ಕೆ ಅಂತ ರಾಮಾನುಜನ್ಗಳು ಹೋಗಿ ಬರ್ತಾರ ಅನ್ನೋದನ್ನ. Let us invest our time, our knowledge and our enterprise into this academic exercise. ಮಾಡಿದ್ರೆ ಬಹುಶಃ ಆಗ್ಬಹುದು.
Okay, sir. Any more questions? Okay, sir. Thank you very much, sir, for your precious time and your knowledge. We are very happy with your talk today. Thank you, sir. Thank you for the participation. Thank you, one and all. We are winding up.
It's my pleasure. Thank you so much.